Now I'm going to start a short demonstration. I'm going to open a Jupyter notebook. It will open with the web browser, and I will go to the presentation mode. This Jupyter notebook helps check 12-digit hierarchical Unicode connectivities and help aid scale model. The files we are going to use for this are channel output that includes annual average stream flow. Also, we are going to use Charkey file with channel information, channel name, channel ID, and 12-digit hierarchical Unicode, downstream object type, and downstream object ID. We converted NH2 plus flowline and water body shapefiles to geopackages that contains COM ID and HOT12 numbers. There might be pros and cons for using geopackages, but I never test loading or reading speed between geopackages and shapefile. But I found that some article and geopackages faster workflow than with the shapefile. One of the reasons why I used geopackage is that I can reduce the number of the files to be stored in HPC because everything is contained in a single file. Then we are going to read all of the files from ABC for each HUB8 model and create the data frame and join necessary data and calculate discrepancy percentage. The next step is to import the necessary library that we can get after we install Holobase. Let's run the code. Then we need to specify paths to data and the file that we are going to use. Those are stored in HPC in USDA Research Center in Texas. Next. This national scale model is running as real-time simulation, so we need to go through them and check their current status. Let's run the code. It takes less than 10 seconds. So we are going to use annual average streamflow data from 2,121 simulations. Next block of the code is all about creating interactive dashboard. First part of the code is about default inputs for control panel. From line 52 is about reading data and it's going to be customized by user inputs. From line 96 is about showing maps on the dashboard, also table and tables header. Lastly, it is about dashboard deployment. Okay, let's run the code. Now you will see a dashboard with a new web browser. Now you can see the control panel on the left and two maps on the middle top and table on the bottom. Maybe we can take a look at Hub 11 and where the drainage of the Arkansas, White and Red River basin is located. Now you can see all the selection have changed. I'll check the table and find the channel that has the highest discrepancy value. Let's sort by discrepancy value column. Okay, the channel named M53196 simulates annual average stream discharge at 99.6 cubic meters per second. And this channel received water from one upstream and the amount of the water is 0.14. Let's narrow down hub 12 level, and we need to find the last 4 digits, which is 1403. And let's zoom in a little, and we can increase the width of channel. Now you see the stream discharge of this channel is about 100, although the upstream is about 0.14. So there might be connectivity issues. We can go back this hub A model, check a modified dataset, and run the model again. You can just refresh the dashboard to see if there is a change. Also, you can download the whole watershed discrepancy table. This is how task came in. Once you handle big data, you want to use a massive cluster from HPC or clouding to do parallel computing. And Dask helps the user deploy cluster of nodes for data processing. To show you the better visualization, let me switch to JupyterLab. And JupyterLab is the next generation user interface that includes the notebooks as well. As an example, I want to extract only a stream discharge output in time series, but I want to have the dataset and output file as hub for scale and visualize them. You can see here we can have 2021 hub 8 scale output, but we go down to 201 for hub 4. Because of time, I will do this with only first 4-digit hydrogen Unicode. Let's run it. You know, there's a lot of Dask application, especially when we use the NetCDF or jar data sets of the climate data or water table or surface water data. Also, there's a community named Pangeo. Okay, it took about 20 seconds. Next one is with Dask. And I'm going to use the 16 cores. And let me set up some charts so that we can see how it works. Let's run it. And we can see we save half of time. Let me show a task tree, but I'm not sure about the name of task tree. But you will see how Dask assigned the nodes for each task. Okay, I will show you one more example. This is the one that I used in the CDF datasets, the annual average simulated crop yields from 2000 to 2014. Also, I used to simulate the text format water contents output, and you can see we have about 35 different crop types and 30 different water contents. Let me change crop type to corn and water contents to evapotranspirations. Let's see how they are related, and also we can see the spatial temporal variations. We have another tab here. It's about checking the national model performance. Then there we get from the water balance simulation output on the left and measure the one on the right. Okay, let's check the evapotranspiration again. And I see there are similar spatial variation, also their distribution. And if you want to check all of the water contents, you can check here, and we can examine them through the scatter plots with the statistics. So far, we've seen some capabilities of the HoloViz and Dask by processing data and building interactive dashboards using the national scale SWAP Plus model. I believe these powerful tools with Python ecosystem and the workflow I've used will be useful to any scientists and engineers, especially who deal with big data and analyze them. Thanks for watching my short demonstration video, and I will see you in the Q&A session.